Okay, here's number 14, even number problem, but it's a good one. So uh, it has 1 to infinity, e to the negative 1 over x, all over x squared dx. So it's another u substitution, but first let me write the limit form. Limit as t goes to infinity, 1 to t e to the negative 1 over x divided by x squared dx. And the u substitution uses the inside function. It's the reverse chain rule, so you're looking for what might be the inside function, and that's that negative 1 over x, which will work perfectly with the x squared in the denominator. So let u equal negative 1 over x, then du is equal to, and you can write that as x to the negative 1 if you like, negative x to the negative 1. Or you can remember that when you have 1 over x, it's a little tiny quotient rule. Bottom times the row to the top is 0, minus the top times the row to the bottom is going to be just 1, since there's a negative, over bottom squared. So this becomes 1 over x squared dx. And that's perfect. It's 1 over x squared dx is already a factor of the original problem. So just the integral again. I'll take the limit at the end. You have integral x equals 1 to x equal to t, because I do have to remember to plug back in. I have e to the u and du, because that x squared dx is already exactly du. Then that's its own integral, so I have equal to e to the u from x equal to 1 to x equal to t. I need to plug back in that u. I have e to the negative 1 over x from x equal to 1 to x equal to t. And now when I'm plugging the t back in, I might as well remember that I need to take that limit. So all of this was just the antiderivative. So now let me take the limit. Limit as t goes to infinity. And plugging in the t and the 1, I get e to the negative 1 divided by t minus e to the negative 1. And now I plug in the infinity. So here it's the rule of limits, where if it's a continuous function, you're allowed to take the limit of the inside function. It's a composition of functions here, e to the on the outside and negative 1 over t on the inside. But it's a continuous function. There's no division. Well, there would be if you were going to 0, but heading out towards infinity, no problem. And then, so you basically take it, turn it into, and it's perfectly okay to show it this way. E to the negative 1 over infinity minus e to the negative 1. As long as you remember that e to the negative 1 over infinity means take the limit of negative 1 over t as t goes to infinity. And so taking the limit of negative 1 over t as t goes to infinity, it takes a long time to write that inside, so you can just plug in infinity. But remember, whenever you plug infinity in, it means taking the limit. And when you take the limit of negative 1 over t as t goes to infinity, then that's a rational function, and the power on the bottom is bigger than the power on the top. The degree of the bottom is 1, the degree of the top is 0. And so when you plug in infinity there, it's equal to 0. And so also you can just memorize 1 over infinity always turns out to be 0. It's the limit as you go out to infinity of 1 over t. So that's a 0. So I get e to the 0 minus e to the negative 1. And that you should simplify at least the e to the 0. It would be all right to leave it as e to the negative 1, but e to the 0 is 1. So that equals 1 minus, and I'll simplify the other one too. It's nice to remember that e to the minus 1 is 1 over e. So this one turned out to be a finite answer, and they do say that the opposite of divergent is convergent. They say that this integral converges. To that finite answer, 1 divided by 1 over e.